Ever felt like physics was playing a prank on you? Well, meet the two-capacitor paradox. It's a real head-scratcher, and we're here to make it less confusing and more hilarious. Imagine this. You have two identical capacitors, both charged to the same voltage. You connect them together. Logic says the charge should distribute, and the voltage stays the same, right? But here's the twist. If you calculate the energy before and after, it seems like energy just vanishes. So you've got capacitor A full of pep and charged up, and capacitor B also charged to the same voltage, ready for action. When you connect them, the voltage across both should still be the same, but the total energy seems to drop. Where did that energy go? Did it just pack its bags and move to a parallel universe? Let's set the stage. We've got two capacitors, C1 and C2. For maximum paradox fun, let's say they're identical. C1 equals C2 equals C, and they're both charged to the same voltage, V. Initially, both are super happy, holding on to their energy. But then, you connect them in parallel. Gasp! The total charge is conserved. But the total energy, it's like a magic trick where the rabbit disappears. But you didn't even know there was a rabbit. You close the switch. The charge redistributes, and the voltage across both capacitors remains V. So far, so good. But if you do the energy calculation, it seems like half the initial energy has just poofed. This is where the paradox kicks in. People scratch their heads, yell at their whiteboards, and question the very foundations of physics. Where did the energy go? Is the law of conservation of energy a lie? Fear not, aspiring physicists. The energy doesn't just disappear into the ether. It's not a magic show. It's just a common misunderstanding of ideal components. In reality, when you connect those capacitors, even if the wire looks perfectly ideal, there's always a tiny bit of resistance. And guess what resistance loves to do? Turn electrical energy into heat. Poof! Half your energy became a tiny bit of warmth. Plus, some of it radiates away as electromagnetic waves. So the missing energy wasn't missing at all. It was just transformed into forms we didn't initially account for in our overly simplified ideal model. Even the tiniest resistance in the wires, or even in the capacitors themselves, is enough to dissipate that lost energy as heat. It's like trying to perfectly slide a buttered watermelon down a grease slide. There's always a tiny bit of friction. The paradox only arises when you assume ideal components with zero resistance. In the real world, physics always wins, and energy is always conserved. It just might not be in the form you expected. So the next time someone tries to stump you with the two-capacitor paradox, you can confidently explain that the missing energy isn't missing at all. It's dissipated as heat and electromagnetic radiation due to the inherent resistance in any real-world circuit. It's a fantastic example of how ideal models can sometimes lead to apparent paradoxes.
And there you have it, the hilarious yet perfectly logical two-capacitor paradox, briefly and hilariously explained. Now go forth and impress your friends with your newfound knowledge. What are your thoughts on this paradox? Let me know in the comments. Don't be a paradox. Share the knowledge. Like, share, and subscribe for more videos that will mess with your head in the best way possible. And don't forget, from Beyonder,